Okay, let's go on to our first real module, if you will, in terms of our quality practices. And the first one, this is really about source code control at a low level. Um, However, in general, conceptually, what I want to talk about is the nature of change and change management. We talked in our agile discussions, we talked a lot about the nature of change and embracing change, but how has change been handled from a tools perspective is really, and a process perspective, is really what I want to talk about in this session. All right. So to start off with, think about a simple task. Let's say you first collaborated on some team paper, some kind of team paper or project at ASU, maybe at work, maybe back in secondary school, whenever. But think of your first true collaboration, particularly when you're working in something in the software world. So perhaps you're working over your email or your Gmail. You're working by sharing a file in Dropbox. You had a Google Drive or a Google site or something like that. All right. What was the nature of change when you were collaborating with somebody? Well, you probably did some stuff, put it in an email as an attachment, and gave it to somebody else, right? And said, "Hey, I got to put this down for a couple hours. You want to go through and put your part into this and send it back." And they sent it back, and they might have sent it back with changing the name to call it version 2, right? And then you change it again and say, okay, here's what I think, and then you call it version 3, and you keep sending it back and forth this way. That's not a managed collaboration in any sense. That change isn't managed. You're just using a communication tool to bounce things around, if you will. But you can't manage the nature of change. You don't know whether somebody deleted something, did something else, whether they just added stuff. You don't know if they lost some of your changes unless you read through all the content, paper, code, whatever we're talking about. So, unmanaged change. Um, in terms of managed change, you're going to say, okay, so now I want to know what kind of changes did you make? Did you delete stuff? Do you have just comments on it? Do you have additional stuff to put in? So you might use something built into a tool. So if you use Microsoft Word, for example, to write your papers, you might turn on the track changes feature, right? And if you do track changes and you're showing those changes on the screen, something happens over there in the right margin that kind of shows you what things changed, what's been deleted. You can even add comments in there and so forth to understand new changes. Inline in the document, there might be kind of strike through fonting or a different color font for the content you added and so forth. And it gives you a little bit of help of tracking changes. And even later versions of Word are kind of internally trying to keep track of when it was last edited and what version it might be. And that's in tool, and that data has to be carried in the document itself. It's not managed external to the artifact. That stuff is actually carried around in a Word document. So if you do attach it to an email and somebody else opens it up, they have all the data to understand change right then and there with them. A different thing, maybe you were working on whatever that paper or project represented was maybe more creative activity. Maybe you were, instead of writing a research paper, you were writing a creative paper. You're writing a story of some kind. And so you wanted to experiment with a new idea, being innovative, being creative. That requires some trial and error, requires some experimentation to things. Well, how do you manage that experimentation? How do you know when you go down with your team, your partner, your multiple partners, down a path where you try something out? Maybe it doesn't work, or maybe it kind of works, and you have to back up a little bit and go in a different direction. How do you manage that experimentation, and how do you kind of know if you've done something before? Or how do you know that you only like part of what you want to do, but you need to morph other parts? How do you manage that? That's a different form of change, if you will. And then sometimes flat out, you just go down that path and you just want to undo something. I went through this experimentation, I went down a solution path, an innovation path, and I just discovered it's not going to work. And for whatever reason, I got to go back to a known point. I have to undo something, go back to a known established point, and go in a different direction. How do you do these things today in the everyday computing tools that you do? All right, think about that for a moment. And then let's think about it in the context of software change. All right. So name all the reasons why software might change. All right. And we've talked about a number of these when we talked about Agile. There's a lot of reasons software change, changing requirements, changes in design, changes in the underlying technology. Customer comes in with a change, your software team changes, you name it. There's a lot of sources of change in the software development lifecycle, right? But now, with that list, consider a few things. And while I talk through this, I want you to think to yourself: are these things you thought about with that change, or did the change kind of happen and you just reacted? Right. So first does your change happen before or after your software product has been released? Meaning you've put it in a customer's hands, right? So there's one thing when you're in the engineering process to have something change. Again, all those sources of change I talked about before. Maybe a bug arose, a defect. Again, common one would be the underlying technology you're using. Maybe you're relying on an open source library, and that changes. Um, but it's different when that change happens after the software's already out in customers' hands, right? Because now the customer's out there, they're using it. They may have started accumulating some kind of intellectual capital associated with your software, meaning they're using your software as a tool, a knowledge tool. So maybe there's a database associated with it or files that are created that represent these things. And now that change that you want to have happen, the bug fix, the newer technology you want to consider, you want to roll out that change. I mean, you want to take and address that change and put it in your customer's hands again. Well, is that going to be compatible with all the knowledge capital they already created with the version that you already released to them? And not just knowledge capital and data, but is even going to operate in the same way? Is there a user experience aspect? Or is there going to be some kind of cognitive mismatch of here's how I used to do something and here's how I have to do it now because you changed the software on me? All right. Do you understand the root nature of your change? And again, some kind of change happens, and if you just react to it, or do you stop and pause and think for a second, what really went on here? What was the nature of that change? Where did that change come from? From all those sources of change we talked about. Again, a defect arose, somebody had a request for a new feature, there was a change in customers' requirements, change in underlying technology, yada, yada, yada. But do you consider what the root nature of that change is? Do you ask yourself if the change could have been avoided? And if it could have been avoided, how? And if not, why not? It was a defect. Why didn't you discover it at the point of injection? Why was it injected in the first place? Why did it make it through test? Why did it make it through verification and validation? So could you have avoided that change being happening at all, and even when it happened? Right? It's one thing to discover a defect while you're engineering. It's another thing to discover it after the software has already been in customers' hands. Obviously, kind of a different ball of wax, so to speak. What is the best way to make the change? That might seem like a strange question, but very often when you have to address change after it happens, there may be more than one thing that you can do about it, and maybe more than one thing that you want to do about it. So again, a defect is a classic case. A defect may be something that you can address with a quick and dirty workaround of some kind, while you worry down the road in the next release of software that you'll redesign something more sustainable. So you actually have two corrections to that defect that you want to roll out. It may be our scenario of technology, the underlying technology change. Some library changes, some framework you're relying on. How do you deal with that? What's the best way to make the change? Do you implement an abstraction layer so you can build an adapter so that you're kind of shielded from those changes in case that happens and protect yourself, or what's called future-proof yourself from additional change? Or is that not the cost of doing that additional abstraction not worth it? And the quickest thing to do is to just rip the old thing out, push the new thing back in, and shove it back out the door. And very often these aren't just technology decisions. These are business decisions. There's a cost associated with that. There's an impact to your customer associated with that, and all these things have to be considered, which is what number 5 is about. Who has to know about the change, right? Did that change cause your user manuals to change? Does your sales force have to name? Does your call center support for your software have to know about the change and what to do? Does your operations team that's managing your software in the deployed environment for customers have to know about the change and what the nature of the change was? Very often with software, you get these release notes that are associated with it. How often do you stop and read the release notes? A lot of people don't, right? The rank and file user normally doesn't because they don't care, but it's that quick and dirty laundry list of what has changed from release to release. Who has to know about the change, what its scope of impact is, what the best way to make a change. All right, all important things to consider in the process. Okay, so we're talking about change management kind of in the abstract at a high level. But what happens when change happens? Some change event occurs, and I've got source code files over here, and those source code files, are going to be affected by this change, right? So what happens there? How do I deal with that? I keep on switching, apologize for that. So some processes involved, some best practices involved. First is, in the abstract, we're talking about change management, and then we're going to talk about some underlying tools associated directly with managing source code files like this. But change management in the general situation is keeping track of requests for changes to the software from customers, developers, any stakeholder, if you will, working out the costs and impacts of the changes, and deciding what changes need to be implemented. So that's what I was saying on the previous slide. The way in which you address change, the durability of your solution, the amount of work that goes into it, whether that's redesign work, whether that's quick and dirty, little design, but kind of a patch, if you will. These things have different dollar signs associated with them, but also different durability in the marketplace. So, who has to know about it? What are the costs and impacts? And who gets to make that decision? The decision, a significant change, the decision isn't the developer, right? It isn't just one person that sits in a corner and says, "Oh, I need to do it this way instead." Right? Now, if you catch something local while you're just in development, maybe you get away with that. But we're talking about things that are downstream. More and more people are aware and affected by your software, whether it's customers, operations, sales, all these people I mentioned before. So now your decision of what happens in order to address the nature of change, that calculus changes because more people are involved, more people are affected. Okay. A specific practice is configuration management, keeping track of how software components and artifacts are assembled, including what versions, how they are configured, and associated metadata to inform a release. What does that mean? Well, just talking about change management in the abstract and what the impact of change is. Well, for you to understand if you make a change to a component somewhere, you have to know in what configurations that component appears. All right, so I have a bundle of code that is compiled into a compilable unit of some kind. It's shipped, let's say, as a library. Now, if that changes, you have to know in what configurations, how it is configurable, and in what configurations that thing may appear. All right, because it's not just a case. And again, for a lot of you, this may not make sense yet, but in a scalable software development process, you don't just develop a piece of code and turn it in for a single solution. You try and make your software reusable. You try and make it operate in different environments. That means normally the thing that you have is configurable. All right, so the headset I'm wearing right now. Right? There's a configuration. I can bring up a menu for you that can show you that, I can turn up and down the audio level on it, for example. That is a component that has a configuration associated with it. The tuning of it in different environments, if you will. So we'll talk more about that. That's one particular process, and you have to be aware of that when dealing with change. And the other part is version management, keeping track of multiple versions of system components and ensuring that changes made to components by different developers do not interfere with each other. So the first part of this, multiple versions of system components. In one sense, when you are developing software and pushing out change, you may have different versions of the same stuff, right? Or I should say your customers may have different versions of your software, right? The next version may have some defect fixes, it may have some new features associated with it, and they have a later version of it that another customer does not have. you got to be aware of what went into what version in order to be able to support those customers in the field, right? Um, the other part, though, of version management is just the actual nature of low-level changes in the context of editing source code. All right, so you know if you have on the slide abc.java, def.java, build.xml, you have those two source files, abc.java and def.java. You and Susie might both need to edit for the purpose of correcting your defect, the purpose of implementing your new user story or requirement. You may both need to edit and change abc.java. Well, how can you concurrently work on that and not clobber each other's work and get both things in? And how are you going to manage the linearization of that change so everyone can keep an accurate history of trajectory of the things that you're working on? All right, that's basically what we're talking about. Going back to the analogy of your team paper, if you will, it's, instead of passing the Word document back and forth between a team member, what if you passed the Word document out to 4 team members at once, and they're all doing edits and changes and sending it back to you? Right? Well, what you're going to get is a whole bunch of track changes stuff in different colors in Word, and then somebody has to manually go through and accept those and decide if any of those clobber each other or don't make sense together. And that's a merge process, and we'll talk about that as well. Real quick, because we've talked about this already in a few places in this course. Change management, the first thing to recognize is that change happens. Every unit of work, anything that you're going to do to your software, requires changing some system artifact. Right? Even if it's a brand new source file for a brand new feature, you're probably going to have to change your build script, right, to incorporate building that new feature and assembling it into the rest of the software to be deployed. Or you're going to have to change the documentation to document the feature or something. Right? So even things that are relatively independent new features still cause some kind of change. All right. A lot of reasons we've already talked about a number of these, so I'm going to skip that. Our change management processes, what do they do? What do they identify? It might seem like common sense, but fairly straightforward. We have to know what system artifacts changed. All right. So, and again, that might seem trivial, except what if you're working in a team scenario on something that evolves very rapidly, like software source code and configuration files, and so you can't just keep it in your heads what's changed. And if you don't have an underlying tool and a process to manage that, and you're just throwing things around, let's say in a shared file system, you probably forget who made what changes when. All right. You're going back through email traces, you're going back through file logs, you're trying to embed comments in the code. None of these things are sustainable or scalable. Why did it need to be changed? Right? So when you go in there and you're tracking a change, somebody might go and say, well, why did they do that? What was that in response to? Right? And again, that goes back to the reason for change. What did you have to do that because the underlying technology changed, because it was a defect that observed? Can you track that, if you will? All right, so that implies a situation where different tools can identify the tasks or the nature of change, and you can reference that in this change management process. Okay, so we'll talk about that. And then finally, who made the change and when it occurred? Do you have auditability? Right? Who did it? Oh, Susie did that. Oh, Kevin did that. Oh, Joey did that, but Joey left the company 6 months ago. Right? If it shows up as somebody who's anonymous or unaccounted for, then you don't know who did it. Right? And the same thing for when it occurred. You need a timestamp on it. You need to know when that happened and how long ago it was. All right? For these reasons and others, change management processes typically require traceability in a management tool. Traceability is the ability to understand, well, it's a couple things. One is the ability to understand dependencies between things. So if A changes, then B will probably change. That helps you assess the scope of impact of change. Right? So some change comes in, you got to change the number of source code files. Why is it that you had to change these 3 source code files over here and not that one? How are those 3 source code files related in terms of its responsibility for a defect, its responsibility for a new feature or a requirement? That's what we mean by traceability. So start with your requirements, go through your design, go through your source code, and kind of be able to create this dependency or connection graph, if you will. right? Part of that traceability helps with other processes as well, such as verification and validation, particularly validation, so you can understand, hey, by the time we get done with this release software, can we trace it all the way back to the business needs, the requirements and business needs, what we were originally asked to implement, all right? Um, the management tool helps us keep track of those traceability links. It helps us with managing the very nature of change. Additional ones, you need to inform stakeholders. All right, you have to let again, I mentioned this before, but you have to let the sales force, the support team, the operations, even the customers know that there's been a change and a change that may impact them. So you kind of have to have some understanding of whether or not that change will impact them. So not all change will. Maybe some customers, some changes can happen that you're totally unaware of. You may have an auto update feature turned on your computer that updates your software in the middle of the night. A common case is the auto update features that go on in my satellite box. Right, I get my satellite TV, and in the middle of the night, periodically, it's going to check and see if something is changed in my program guide, in my plan, or something else, or in the services that they offer, the apps that they offer through the box, and that auto update happens automatically. And are they going to let me know about it? Are they next time I power on, are they going to tell me about the change, or am I just going to discover it the next time I go to the program guide? It says often there's a CCB, but I didn't spell that out. What do we mean by CCB? CCB is a change control board. A change control board effectively is a representative population of folks of stakeholders in the project who have to be aware of change and who participate in that decision-making process. So, again, hypothetical. Um, your software is operating. It's been released in the hands of several customers. There's different versions of it. Perhaps you have different vertical domains your software relies on. So you got a salesperson representing the North American market and a salesperson representing the South American market. You got a salesperson representing your product in education and another salesperson representing your product in healthcare. But it's all sharing the same software. All right. They have a stake, right? They have customers that are paying money that they're responsible to listening to, and frankly, they're trying to probably upsell to. And so, if you come along as a developer and say, from an engineering perspective, it would really be great if I could take this brand new gizmo. Right, Gizmo again might be an open source library, a new infrastructure technology component, a new version of your Android operating system, what have you that you have a dependence on, and I want to slide in and make an assumption that we'll work on this new thing because that'll make us that much faster, that much better, that much whatever. From an engineering perspective, that may be a slam dunk to you, but that salesperson is going to think about, well, what's the impact of my customers? How am I going to inform them of the change? Do we have to migrate data into change? Are they going to be upset because we change too often? Is there changes to their interaction with the software? How is it going to affect their business? They're thinking about them. They're not thinking about you as the engineer. They could care less that you got a new gizmo to slam in there. They care about their customers. So what happens is there has to be a collaborative decision made in the best interest of the organization, a change control board. And so the change control board may decide, no, you can't actually incorporate that new thing, that new technology infrastructure now, but you can do a small version of it here for existing customers, or maybe you can change it for future versions since those aren't released yet, and you're going to have to defer what you want to do until our roadmap plan a year down the road or whatever. All right. So change management control, who's even on it depends on where your software is in the process. I've seen change control boards evolve with the product as it gets closer to release, so it may be made up of some internal people initially, and as you get closer and closer to release or even get post-release, we'll start incorporating more of these customer-facing people in your organization. All right. Switching gears, and now I'm going to drive. That's change management. Again, in the general, in the abstract, I'm doing a lot of literally hand waving about it. I know, and again, that's because the nature of change is so broad that the processes at the high level have to be relatively broadly defined. But what about some specific practices, some specific things that you do? The first one we mentioned on a previous slide with some of the definitions of terms was configuration management. So one of the things that I want you to look at is section 3.3 of IEEE 828-2005, the IEEE standard for change management on software projects. And in that section, it talks about 7 software configuration management activities. The first activity, configuration identification, identifying what needs to be controlled. All right, and in the specification itself, in IEEE 828, it actually lists just about everything you can think of, from source code to documentation to configuration files to databases to project management plans. You know, pretty much if it's associated with the software product in any way, it pretty much says that you need to identify it. What does it mean to identify it? It means to give it a name and to know a specific version of it. So it can be uniquely identified, and the version that you're on can be uniquely identified. All right, so that's configuration identification, and normally things that are identified are considered to be a CI. You see CI in the next definition for configuration control. A CI is a configured item or a configurable item. All right, so the identification process has to identify all the configurable items. Configuration control: request, evaluate, approve or disapprove, and implement changes to baseline CIs. That's direct quote out of the standard. This is kind of almost like the CRUD operations you would do on a piece of data. The configuration control aspect is, how someone goes about requesting a change to something, who, when, where you evaluate that change, who gets the decision-making authority to approve or disapprove that request for change, and again, maybe that's a change control board, and then who implements the change to these baseline CIs. And again, baseline here means a known point. Someone's going to request a delta change from some known point in your software product. All right. Configuration status accounting, and this is basically the status activity. It's really how you track and can report out what the status of each CI, of each configure item. All right, so you're able to give its history. You're able to report on what state it's in. You're able to report on whether or not you're in an approve or disapprove process, or you're in the middle of implementing changes in the configuration control process, things like that. Right? Configuration evaluation and reviews. Direct quote: a management mechanism to evaluate a baseline. And again, we talked about a baseline being a known point. So the evaluation and reviews are your ability to review those things and really establish a baseline, if you will. Interface control. Interface here is not meant in the software interface thing. It's meant as the human interface, the team-based interface. So this says coordinate changes internally with changes external to the project. That's not really worded very well. But effectively, some change is happening internally in your team. How do you, in your product, and you may have your local CCB and everything else, but still your changes may need to be communicated external to your specific project. So, your change control board decided on your project, this change is appropriate, it's been approved, you're implementing changes, you have a plan to push it out to customers and all the other stakeholders, your support people, your operations people. Interface control is saying, how do I coordinate those changes with other projects in case they're going to have a similar problem, in case they have an implied or explicit dependency on whatever you've changed. And sometimes it's even a little bit tighter than that. It could be another team working on a different component in the same project. And maybe the project has an overall non-functional requirement to operate, let's say, within a particular memory footprint, right? And if you have a component that operates in a certain memory footprint, and they have a component that operates in a certain memory footprint, and you increase your footprint, are you jeopardizing the overall global non-functional requirement of the entire application's memory footprint? So for these reasons, there has to be some way of communicating change and interfacing to external projects, external stakeholders. A special version of that, subcontractor vendor control. How you plan and monitor change that happens with your subcontractors. Again, in any reasonably large development, very often pieces of work are farmed out to a subcontractor to help. that subcontractor, I mean, you may have a very tight relationship where you ask the subcontractor to work directly within your tool set and processes. Um, However, very often you're kind of, cutting off a chunk of work, a piece of the pie, if you want, handing it to them, and they may have their own process for how they develop software that's not exactly the same as yours, but still you have to plan and monitor change that happens with them, because you're, as the prime, you're overall responsible for the project. So if you handed them, hey, here's some work, and here's some starting software artifacts, you go, figure out this sub problem for us. You want to know what things have changed, all right, and how you monitor change, and again, whether that change that they're doing impacts what you're doing, or vice versa. And then finally, release management delivery. How the build, release, and delivery of software products and documentation will be formally controlled. And that'll be somewhat implied when I go forward and talk about some specific configuration management things here in a slide or two. One of the things I wanted to point out, when you read through the IEEE standard, developed very smart people. It's a 2005. This has been, but there were versions even before that. The main thing when you read through that section is, count how many times you read or hear the word implied controlled. We talked about it with Agile. That a lot of the predictive, prescriptive process models have try and take tremendous effort and add more overhead to try and either eliminate change or really kind of draw a bounding box and control change. All right, and they haven't always been successful. In fact, very often they haven't been successful in other life cycle models, and realize that they realize that change is a big risk. So it's all about trying to control it. Whereas Agile says to embrace it. Okay, implied in here when you look at these 7 SCM activities, when you hear me talking about traceability on the previous slide, that's the nature of overhead that I'm talking about when we talk about an Agile process, trying to reduce that overhead. Your tool is asked to do a lot more stuff. You have to keep a lot more metadata associated with things. Configuration identification, versioning information, the status of stuff, when it's been reviewed. You have process overhead in all these interfaces and change control boards and the like. So all this overhead kind of weighs everything down and can make you move slower, right? So Agile can't magically do away with all that, but it tries to take a more approach where we know change is going to happen, so let's talk about ways to embrace that, to enable that to happen, as opposed to using the word control, which suggests to me some kind of constrainment of change. All right, let's drill down another layer and start talking about some specific terminology associated with configuration management. So we've gone from change management into this first part of configuration management. Configuration management is a management of software artifacts or components, assembly, and configuration. And I'll talk on the next slide. I'm going to go to it right now, what a configuration is. A configuration, an instance of a system composed of specific versions of its artifacts. So, a configuration is just that. It's an arrangement. Think of a musical arrangement or something like that. You identify the different software artifacts that go into that particular configuration. You determine how they need to be customized, tweaked, tailored, configured, meaning perhaps parameterized values given to them so they can work in specific categories or specific instances of target environments. The one that works on, my Android phone version 4.4 versus my older previous phone version 4.0 versus my previous version 2.3. Oh, and, can I take the same thing, and for some of my apps I can, go over and run them on an iPhone, or can I run them on a tablet? And so do I need a different configuration of that? Are there some different artifacts involved, or are there some changes to the parameterization or settings that I have to use in those runtimes in order to get the software to operate in that environment as expected? All right? That's what I mean by configuration, arrangement, composition of artifacts. All right? So with that in mind, configuration management is the management of that assembly and configuration process. Understanding, what arrangements are possible, are practical, what arrangements go to what environments. That's what configuration management helps you do in a general case. Some building block concepts so we can kind of understand how to build those different configurations. First is the notion of a code line. A code line defines a trajectory for source code artifacts. A trajectory kind of means a history. All right. The software is evolving, and it should be evolving in a particular direction. One of the things in your requirements class that you'll talk about, actually you should have talked about a little bit in your design class, is the notion in design of assigning a responsibility for something to a particular object or component, whatever that unit is you're talking about, a file, a function, an object. I'll just use the word component. In design, our goal is to assign responsibilities for certain things into components and then arrange those components, if you will. But from an individual component's perspective, it should be dedicated to that specific responsibility. If it's dedicated to more than one responsibility, you actually have a design flaw in your software. Right, and then we'll actually talk about cohesion and coupling later in the semester, which are related notions. But in any event, you have this notion of this trajectory, you have this notion of this history, meaning as different change happens, you started off with something and delta change keeps happening, as you can see from code line A, B, and C, to create new versions of something. All right, and then finally, you have a set of policies governing participation. I'm going to talk about that in a couple places, but let me describe kind of what I mean by that. 3 different code lines, A, B, and C. On this abstract diagram, I haven't even told you what those code lines represent. All right, do they represent related components of software, the same thing at different points in time? And it's actually not important for the conversation. What's important, and let's just assume for now that they're different components, but what's important is I have a trajectory, I have a history, I have versions of them going left to right, forward in time. Whether a piece of software gets to be on a particular code line, there has to be some policy governing its participation. That policy is normally defined from a quality perspective, meaning the software component, the artifact, has to exhibit certain quality attributes in order to be included on the code line. This is a very important concept for us in this class, and it's an important and sometimes under-practiced concept in industry. What I mean by that is you may say that code line A represents releasable software to the market, therefore we have to have all critical features, however that's defined, unit tested. We have to run a full static analysis. We have to have 60% of the code individually code reviewed, maybe 100%, whatever you want. But normally those policies are defined by very specific quality activities and quality measures that the software achieved. And if you don't achieve it, then it doesn't happen. And I don't know why I just jumped out of this. I didn't touch anything, so I'm going to go back into it. Apologize for that. Okay. So again, that's policy, and I'm going to come back to that concept in a minute. And then finally over here we have a baseline is a named configuration of stuff. So when you look at the configuration, it's an assembly of different versions of these different artifacts from different code lines and from different libraries of external components that you don't manage. And that establishes a baseline. We're going to name that baseline V1, and that named baseline has that named configuration, a named arrangement of specific components I'm pulling out of my code lines. All right, and a different one for V2. Okay, a configuration itself, an instance of a system composed of specific versions of its artifacts. I talked about that a minute ago. I kind of jumped over to this slide. Wanted to remind you of what a configuration is because it's important, because from the perspective of a release is an instance of a system distributed to users outside of the development team. So a release is, and sometimes folks say internal release, but it's at least off the development team. It's given to customers, internal or external, that are actually going to operate the software. All right. The point is that what a release really is a named configuration that's intended for that user population and typically intended to operate in a particular target environment or subset of target environments. So again, going back to my Android device, I may have a particular configuration that I'm going to name as the release that goes out, and I got to go put it on Google Play Store in order to get my app delivered, and it's meant specifically for KitKat. That's the version of my phone right now, version 4.4 of Android. But I may have a different configuration, and I need a different release for an older version of Android. And so I've got to do something different on the Play Store to address that version of things. Okay, so a release as a named configuration that's put in the hands of some kind of internal or external community or customer group. Additional concepts: version management. We talked about version management up front. This is a relatively common concept. Keeping track of versions of software components or configuration items. There's those CIs again. And the systems in which these components are used. And very often version management part is really more concerned with the former, keeping track of the versions of the components. The configuration management will track a little bit more what systems these components might be used. That way, if you're worried about some change to some subsystem, you may know what version of a software component to go back to. Really, the point of version management is to ensure that changes made by different developers, different engineers to the different versions don't interfere with each other. All right, and we're going to talk a lot about that. Version management in software is what we usually think of as source code control. And we'll talk about different tools. We'll talk about different ways that is in a minute. But effectively, now we're envisioning a tool where Kevin, Susie, Joey are all working on the same software artifacts, and this version management system, this source code control system, is going to help me track the different versions of things, track the change, understand what different people are doing, help me even merge or correct when different developers are happen to be working the same area code at overlapping times. So this is the kind of features that source code control systems provide. A source code control repository. Well, and again, and I'm going to point this out as we go forward into some of the details. Source code control, the nature of the tools has changed a lot over the last decade, even more recent, more half dozen years, I'd say. So some of what I have in here I'll point out is some traditional thinking about the way source code control is done, and then I'll try and point out some place where there's newer ways of thinking about how source code control is done. So traditionally what you would have is a shared source code control repository, normally sitting on a server somewhere. Could be a shared file system, but normally sitting on a server that basically is the ground truth. It has all the actual artifacts, source code control, source code artifacts of your source code product. It could be, again, a shared file. Like there's something called Visual Source Safe that would work on shared file systems, client-server tools, CVS, Subversion, these kinds of things. It usually provides some mechanism for assigning jobs to change control. What that means is you define a job. A job is a job. It's an amount of work. But in order to complete that job, you have to enact change on more than one software component, many software components at once. That's a little different. The very first generation of some of these tools for example, on Unix, you had the RCS, Revision Control System. Evolved was the basis for CVS, Concurrent Version Control System. These things were file-based. So basically each individual file was changed. A job-based one basically is almost transactional. It implements a change of a collection of software artifacts together and associates it with a logical piece of work called a job. For example, Perforce does this kind of thing. But again, I'm trying to paint a picture where and I'll have some diagrams in this where you have this centralized repository of your software, and you have individual developers working on their little workspace, as it's called, on these things, and all giving their changes back to the mothership in order to manage change control. I mention that because that's a little bit different than some of the thinking nowadays that has evolved with Git, with Bitbucket, Mercurial, things like that. where you have content addressable file systems that are used. So now, and those support things called distributed version control systems. The nature of storage space and bandwidth nowadays and compression algorithms, frankly, is that in these systems you have an entire copy in an object-based hidden file system of your artifacts, and those artifacts are not referenced by some this logical identifier. They're kind of self-addressable. They're addressable by the content that they hold. So effectively, they're hashed and they're stored with those kinds of identifiers, and that's how they're indexed. So you have whole copies of repository objects locally instead of just your delta change management. And I'll talk a bit more about this in a little bit. Additional CM concepts: workspaces are local client repositories. This is where the developers work. So these are the clients. This is where you're actually doing your code editing and so forth, which means you're working on your copy, and the mothership, if you will, that has the server has a source code control repository, which means periodically you've got to go out and sync with that repository. Old way of thinking said you kind of had to sync often in order to minimize the granularity of change and reduce thrashing and merging, as well as protect yourself, if you will, kind of a pseudo backup system. Again, newer thinking actually says, no, we're going to treat these things as peers, and I don't have to sync as often as I used to. A branch is a named variant of a code line. All right, so branch still is a collection of software artifacts. It still has its own logical identifier. You refer to a branch by a name. Branches are typically not meant to last forever. Your main code line, or what's often called the trunk, is the main. It's called the main code line because it's the main trajectory of your software over time. And in theory, you give it an infinite timeline, an infinite trajectory. You have a roadmap for your software product, and the main code line represents the direction of the innovation in your software. A branch as a named variant is a way for you to partition out from a known point in there to say, okay, here's a point, here's perhaps somewhere where we need to go and experiment. We want to try one of those experimentations and see where it goes for innovation. Or maybe I've got something I've already given to customers and I need to keep this variant around because I've released it into the market, so I have to go back and be able to recover it, even though I may be changing things as I go forward in the new release. A branch can be maintained indefinitely for release, but even releases eventually are deprecated and customers are pushed onto the latest release of something. Hey, goodbye last year to Windows XP. Eventually all good software goes to rest. So that branch can go to rest, or it's meant to be folded back into the main code line. So you're doing that experimentation. You find out it works, and some of this, this innovation you want to keep and roll back into the main product, which means you've got to, in a sense, copy it, or what's called merge it back into that main code line. And we'll talk about that a little bit more in a little bit as well. A label is a tag identifying a specific version of an artifact. A lot of systems now do some form of tagging. Tagging is kind of a way to, by assigning this logical identifier to something, you're identifying a group or a collection of artifacts. All right, it's a way to say they're related outside the normal mechanisms of a branch or a configuration. So that the way it's used in configuration management or source code control system, a tag is normally used to help you baseline a known point in the software that you may want to come back to. All right, so it's a checkpoint, if you will. It's a way to journal and come back to some known point you were in the software without having to create an additional branch. All right. A branch normally, as a variant, by the way, has its own tag associated with it. Normally you branch and tag at the same time. But you don't always, you don't exclusively tag only when you branch. You can tag without branching as well. And then finally, optimistic versus pessimistic, the version management mood. If you are optimistic, you allow changes to artifacts checked out by collaborators and trust them not to clobber each other's commits. If you are pessimistic, you lock resources to allow sole editing. Most folks are a bit more familiar with optimistic. What that means is, Susie and Kevin are both working on abc.java in their own workspace. They can go ahead and do that. and they can submit their changes up to the source code control repository. Now, if there's a problem, if they change something in the same area of the code, there is going to be what's called a conflict that has to be worked out, because the code can't be merged, meaning those two different changes have too much overlap for the system to actually figure out how to put them together, and some human beings got to get involved. In most optimistic source code control system, that human being is whoever is trying to commit a change last, because the other change already made it in. A different flavor of that is in some, again, Visual Source Ace was an example. You could also have pessimistic or locked resources, meaning somebody said, I'm going to go edit abc.java. The server knows that. They know they've handed out that copy, if you will, into some workspace, and they're not going to give you a copy. They're not going to accept any changes you might try and make, even if you do have a copy somehow. That lock belongs associated with a particular person, and essentially you're linearizing the process. Pessimistic would be used in small teams and small systems where you don't want to have to deal with a lot of merge conflicts. You're going to be working overlapping in this source. You know the nature of the changes are very mission critical. You have a relatively small change, and so you'd rather just let one person work on a sensitive area and commit their change, because you can identify it more readily. It's a sequential, linearized type of process, compared to an optimistic one where, again, multiple people can be concurrently working on something at the same time and can submit their changes, their change sets, at different times that overlap, and therefore somebody's got to work out how those changes go together. All right. Optimistic is more popular because it enables throughput. It's a faster way to work, and working fast, time to market pressures are normally an overriding concern for most software projects. So those are definitions of concepts. What are some configuration management best practices? First, we talked about the notion of policy before. Define for each code line a policy. And I want to spend a couple minutes here. Again, a sample code line policy may be we've unit tested and can show we've white box unit tested and shown that our code coverage is above 90%. So I worked on an open source project, igsdk.org, Image Guided Surgical Toolkit, and we had different policies for code coverage based on whether you were on the main code line for the product or whether you were on an experimental or dev code line. So we had levels of like 95%, 70%, even 50% of code coverage on our unit tests, because obviously the more unit tests you write, the longer it takes you. However, it's ensuring better quality. Same thing with your static analysis tools. Same thing with your code reviews. And these are all quality practices we're going to talk about this semester. But you define that policy in terms of those quality measures, and if the software doesn't achieve those measures, you reject the change that somebody is trying to submit. So if that developer can't prove that it's been code reviewed when it was supposed to be, can't prove, if you will, that you have 90% white box unit test code coverage, if they can't prove that you've run your static analysis process and you have no priority one issues from the static analyzer, then the change is rejected. All right, even if the developer can show it meets a functional requirement, right? Maybe you have an automated test tool that can show that yes, this thing actually does what the requirement said, and we need that requirement implemented in the software. You can reject it because the quality policy says that the quality of that software they're submitting is not up to the agreed upon standards for this code line. And again, I don't say for this project, I don't say for this team, I say for this code line, because it is possible for you to maintain multiple code lines, individual main lines, different branches, in the context of the same project. And again, for experimentation, you don't need all those code reviews. You don't need all the unit testing. You don't need to run static analysis. You're trying to figure out if some idea you have works. You're working innovatively. You want to work fast. You're kind of working in the moment. So you don't want the heavyweight process slowing you down. So when you're out there working on that experimental branch, your policy may be much less, even non-existent. Okay. Another best practice is to give each code line an owner. There should be a name associated with each code line. I don't know that this is necessarily a best practice that I see as much anymore. Very often code lines are owned by teams. But when you get into a situation in traditional source code control systems where you have, and you can see it down below, a lot of branches going on, normally you want to be able to know who's the person that's enforcing the quality possible, who's the person who's responsible for that code line, so I can understand why that code line even exists. It's a fortunate case that long-lived code lines certainly happen in my organization. Sometimes folks even forget why they're there. And the more of that you have, more of those code lines you have around, the more branches you have around, it becomes noise in the system. You start to lose institutional knowledge of why it exists and whether it needs to be maintained. Because realizing when you look at this code line and branches diagram down here, the more it looks like a kind of a fishbone diagram, the more of those offshoot points that you have, the more when change comes up, the more places you have to go across those branches to see if that change applies to you. So there's typically a process of pruning those branches and trying to restrict and not over branch or branch too often. That's why some of the best practices down below, because the more you branch, the more you have to deal with the impact of change and understand it. All right, and then finally have a main line. And actually, looking at the diagrams down below, the one in the very lower right that says no next to it, is considered a bad practice because you don't really have a main line. The main line that says version 1 terminates, and instead it's the branches that evolve over time. All right, and you lose some history about that, and you don't have a single trajectory there. All right, compared to the first one over time, which always has that main line, always has that trunk, always has that direction or trajectory that your software is pointing in. All right. Best practices: change propagation from one code line to another. Make original changes in the branch that has evolved the least. So the shorter the branches over time, normally makes testing that original change easier, and normally that's the most important customer base or trajectory base. That's not a hard and fast rule. That's kind of heuristic, if you will. Get the right person to do the merge. If you have conflicts, when you try and merge versions of a source code artifact together, you really need somebody who's very familiar with that file, object, collection of objects, whatever it is, that unit of work, to do that merge. Because if you have somebody who's not knowledgeable with it, they might do the most expedient thing possible without understanding what the full scope of that particular software artifact is dedicated to. Propagate and merge really early and often. So it's kind of a, you want to, what this is trying to say is you want to detect change as early as possible. You want to keep change as small as possible. And the reason why is these merge conflicts I'm talking about, these delta changes that have to be integrated back into another branch. The bigger they are and the more they've deviated, all right, you've driven down a road, now you're deviating. The more distance you go, the more painful that merge process is going to be. So instead, the best practice in traditional, again, I'm talking about traditional kind of centralized pattern of change control, is to propagate early and often, to manage that change in small chunks and to do it frequently rather than to let the change grow and deal with a big merge. The level of effort tends to grow exponentially. Branches are, again, variants of code. We talked about that. What are some best practices around that? First, don't copy when you mean to branch. So you want to experiment on something and you are working in your workspace in your local file system and you say, oh, I got this idea. I want to go mess around with it real quick. I think I'll just go do a recursive copy of my entire directory and just move it over here and start messing around with it. Right? Well, now you're working outside of the change management system. So you can't achieve any of its benefits. You can't share your experimentation with anybody else. It's not backed up. It's not versioned. None of these things are being tracked. You're working out. I mean, change control system, a source code control system can't help you if you're going to work outside its boundaries. And that goes, you know, for not just branching, that goes for a number of practices. Working outside of that, then you lose all the benefits of having it. Branching only when necessary. So again, it's relatively easy in traditional tools to create a branch of something. But if you branch too often, again, you get this unwieldy structure where it's very difficult to manage the nature of change across all the branches that exist. And again, it's hard to manage. You lose track of it. You don't know who the owner is. You don't know whether or not you're supposed to terminate that branch and get rid of it. All these kinds of things tend to evolve over time. Branch on incompatible policy. Again, talked about the notion of policy. You may not even have an explicit change, or it may not be a new feature or function or requirement that comes in as a variant. For whatever reason, you may need to change the quality policy around something. Maybe you have a specialized customer of your software, and that customer doesn't require the same amount of quality policy. Maybe you've been ordered to integrate a new feature quickly and to deprecate your policy, meaning don't apply it to the main line, and you might say, okay, we'll just go ahead and do it. Well, don't do that in the current code line that's maintaining that policy. Branch, create a new code line, that new variant, and go ahead and define the quality policy appropriately to meet whatever process and delivery requirement you're under, so you don't pollute the level of quality associated with your code. In a particular code line, all the code should meet the quality policy. And so if you start mixing it and saying, so, well, some of the code doesn't because we had to work fast, you basically invalidated the entire code line. So branch on incompatible policy. Branch late, merge early. That's kind of itself a variant on branching when necessary. Try to again, it's kind of the thing of not creating too many branches, not automatically thinking of creating a branch. Only branch when you need to, and branch as late as you can in the development process as possible. And the reason why is if you branch early, again, any divergence eventually at some point is going to have to be reconciled. And the more divergence it is, the more it grows separate from the main line over time, the more painful that process is going to be. That's also why you merge early. Branch late, meaning, wait until the last possible moment. In fact, if you have other things going on, are going to go into main line, you can get them in first and then branch. That's better. Try and keep the branch as short-lived as possible and merge it back in. If the intent is to do your experimentation or to do a defect fix, in a sense, branch as late as possible, do what you need to do, and get it back in. Don't let the branch just hang around and start doing additional things on it. All right. And then finally, branch instead of freeze. The whole point of this, a significant point of this is, you don't want to go to your team and say, hey, we want to try out a new idea, so you all have to stop development while Kevin and Susie go off and work on this idea and see if it works. And so we're going to let them do that, so none of you guys can push changes into the main line, into the trunk, and you have to wait for them to get done, and we'll see if they're successful or not. No, it's supposed to enable folks to work concurrently on different requirements, defect fixes, quality policies, releases, whatever the reason, and to keep everybody moving, keep that momentum going, instead of saying, hey, you got to freeze, you got to stop what you're doing. That inertia is not good in a software development process. these particular branching assumptions, and even several of the things I talked about on the slide, realize that a number of the best practices I talk about is taken from 180 reading, the Weiger's reading, and it predates what's going on now in distributed version control systems. And so some of these assumptions will change because we'll have a concept of more flexible workflows associated with change. So you don't always just have to do it this way. This gives you a different view of the branches and merges of the figures on the previous pages. What this is, again, this is something that will change as well. This is kind of the model that's been understood in centralized source code control systems for, I don't even know how, a long time. And that is that you have a main line and you do a branch, what's called a branching and merging workflow. So at the top, you have one code line. If you want to manage versions on that one code line and make changes on it, you can, but effectively you have to lock. Again, that's the part where you're locking means you're freezing. You're going to linearize the change and you're not going to allow folks to work concurrently. You're not going to have more than one release. So you're going to have some restrictions on the rate of change you can handle and who can do change at what time. In the next figure, you see concurrent developing using branching, multiple code lines. Now we have a main code line, that's the one 1.1, 1.2, 1.3, and the branch, which even notice how it's numbered, 1.2.1.1, 1.2.1.2. Since we're branching from a known point, 1.2, our branch numbers start a new dot number of .1, and then have its own subversion underneath that, the 0.1, and then the next one's 0.2, and as you might imagine, the next one will be 0.3. That's now a branch code line. That branch would normally have its own logical name associated with it. That branch, again, we don't know from this diagram if that's for experimentation, to handle a release for a special customer, to do a defect fix or whatnot. But we do know now that the code actually is supporting two concurrent trajectories. So the purpose of the main line of that first line going across the bottom is innovating on the future release of the product as a whole. The point of the branch version is to support a particular dedicated purpose, release, defect, experimentation, or whatnot. All right, but both exist. Now, eventually, though, you may find and do some kind of change in the branched, all right, and that maybe that's a really, let's say that 1.2. The branch in 1.2.1.1 and 1.2.1.2 represent released software put in the hands of customers external to the organization. And as that software is operating, a nature of change comes in. There is an incremental feature request that your customer base has asked for. And you need to put it in already released, meaning you have to put out some kind of workaround or patch, or perhaps a whole new minor release out on your website of that software for auto update, let's say. And so you work on that in the branch. So when you go from version 1.2.1.1 to 1.2.1.2, there was some delta change to some set of files associated with that you wanted to push out into the marketplace. But whatever that was turns out to be a feature that really should also be incorporated into all future versions of the product as well. You need to incorporate it into your roadmap, if you will, which means you've got, in a sense, copy it back down to the main line where you're doing that innovation. So that process is called a merge. You see the dashed arrow for the merge there. That merging, now what happens though is you branched at 1.2 and you diverge, and now there's been additional change on the main line from 1.2 to 1.3, while at the same time being that change on the branch. So when you merge, if there's something that happened in that space between 1.2 and 1.3, whatever those changes were, then when you try to go to 1.3 to 1.4 and merge those changes in, maybe they conflict. Maybe they touch on the same areas of code that the change from 1.2 to 1.3 did. All right. So again, If it didn't, then the merge is normally straightforward and usually can be done automatically with today's source code control tools. However, if it does touch on the same area of software in different ways, then you're going to have a merge conflict. Normally, most source code control tools, what they'll do is they'll tell you there's a conflict, and they'll even highlight what the diff is, the difference is between the two changes in the files. But then you need somebody knowledgeable to go in and resolve that and determine how both those changes can be incorporated. And who knows, you may even have to retroactively go back and change the branch for that. So again, this shows you a fairly simple example where there's been a minimal amount of change that the branch and merge are presumably, we don't know what the unit of time is here, but presumably happen relatively near in time with not many other intermediate changes. If this branch has lived on for months, years, and there's been a lot of changes to your files, and there's been a lot of changes to the mainline files, and then you try and merge, you're more likely to have a conflict. It's more likely that something has evolved or changed over time that eventually when you try and merge a specific change back into something that you've diverged from for so long, chances are more likely that you're going to have a merge conflict that you're going to have to resolve manually. And it might even be fairly laborious to do that manually just to get that thing back in. Okay, I'm going to stop this particular video here. In part 2, I will talk about some newer thinking around version control systems called distributed version control systems. That will lead into a specific discussion on Git, as Git will be the tool that we use during the context of this course.